Okay, I almost forgot. We looked at acceleration using velocity time graphs, but I also wanted to look at it a couple different ways. The first one being a position time graph. And if we have our velocity time graph, we can kind of translate that into a position time graph. So if we have something that's accelerating and let's say it has a positive acceleration, remember the slope of a position time graph is the instantaneous velocity, or rather the I guess the velocity for a given interval. So what we see here is that we should have a slope that is non-zero, and it should be increasing in the positive direction. So we should have maybe something that's already going up, and it should be getting greater in magnitude. So we can see that it's kind of a curve. Okay. So if you see a curve on a position time graph, that tells you there's acceleration going on. Notice the velocity time graph doesn't tell us a particular position, so this curve could be happening down here. It could be happening up here. If we started out with this as our graph, and let me do that in a different color. So let's say this was our graph. Then we can see we have a negative slope at first. We should have a zero slope in the middle and then a positive slope. So we should have a negative slope, zero slope eventually, and then a positive slope. So we get kind of a parabola in this case. But again, we don't know where that starts or where it ends. If we take vectors, we can also look at acceleration in a different light. So let me erase all this. So we defined average acceleration as the change in the velocity for a given unit of time. And we can rewrite delta V as one velocity minus one from earlier, and or 2 times for those velocities. These two are vectors, so we can see if we take the two vectors and subtract them, we can get the vector delta V. And this helps us because the change in velocity, its direction is the same as the acceleration's direction. So let me give you an example. Let's say this is my V naught, and perhaps we're going to speed up. So we should be going in the same direction, and we're going even faster. So this is V. Well, mathematically, we want V minus V naught. But this is how we would arrange them if we're adding them together. But we're actually going to subtract the V naught. So another way we could rewrite this is V plus the negative of V naught. So we can add V to the negative of V naught. Negative V naught would look something like this. We can't add this way, we need to add tip to tail. And so we can see here our acceleration is in the direction of v, because our change in velocity is in the same direction as v. Let me give you another example. So let's say this is v naught. Yeah. So v naught. And we are going to slow down instead. So v not as fast. So again, we want to take v and add the negative of v naught. So v, and we'll take the negative of v naught. And we can see here delta v is against the direction that the object is actually moving in. So if we're speeding up, like this case over here, originally it looked like this, with slow speed, then fast speed. If we're speeding up, the change in velocity is in the same direction as velocity. If we're slowing down, the change in velocity is against our direction of motion. Okay. So what that tells us is remember, acceleration shares the same direction as delta v. So if delta v is in the same direction as our velocity at the current time, so we'll say v naught, it should be speeding up. So even if they're both in the negative direction, they're still speeding up. It's just they're speeding up, the object is speeding up in the negative direction, whatever we define that as. So we can think of maybe positive as speeding up in the rightward direction, and negative here, maybe the object is speeding up in the leftward direction. But when delta v is against the motion of v naught, so here delta v is to the left, v naught is to the right, that tells us we're slowing down. So when the two, when the velocity and acceleration, when those signs agree with each other, the object is speeding up. When the signs disagree with each other, they're slowing down. And so that's one way we can look at acceleration.